words about, okay. Okay, well, good evening. Good evening, everyone. It's a really great pleasure to be here tonight to share with you some recent discoveries in star formation, which has been the focus of my entire research career. And these discoveries have been enabled by the synergy between two very powerful telescopes, the James Webb Space Telescope, JWST, and the Atacama Large Millimeter Submillimeter Array, also known as ALMA. So today's talk is organized as follows. After a brief introduction to the observational background, we will learn about our currently accepted outline of the star formation process based on observations acquired over the last 4 decades. These observations were enabled by the advent of infrared and millimeter wave astronomy over the same time period. Next, we will learn why JWST and ALMA are playing pivotal roles for making progress in the detailed study of star and planetary system formation. Finally, we will present recent results for two systems in the same nearby star-forming cloud, a protostellar system just a few 100,000 years old, and an older, more evolved, but still very young, 2.5 million year old multiple system. Both examples will highlight how complementary JCMT and ALMA data are. So the purpose of this slide is to give you a taste for what JWST and ALMA can see in relation to all forms of radiation that make up the entire electromagnetic spectrum. It wasn't until the middle of the 19th century that it was understood that the light our eyes are sensitive to is just one form of electromagnetic radiation. The fact that heat, light, and radio waves are different wavelengths or energies of time-varying, oscillating electric and magnetic fields traveling at the speed of light was first experimentally verified as recently as 1888. All of astronomy was done at visible wavelengths until the advent of radio astronomy in 1930, followed by near-infrared, millimeter wave, X-ray, and gamma-ray astronomy starting in the 1960s. The insets at the top of the giant elliptical galaxy known as Centaurus A show the difference between its appearance at just visible wavelengths at left and in the combined light of X-ray, visible, and submillimeter wavelengths at right. At the bottom are images of 3 space telescopes and ALMA, arranged in order of increasing wavelength from shortest to longest, delineating the spectral regions each can see. Can you see that okay? All right, great. This slide summarizes in tabular form the many reasons why both infrared and submillimeter millimeter observations are required to probe star formation. First, we need to be able to see past the intervening interstellar dust, which obscures the sites of present-day star formation. The longer the wavelength, the deeper we can see into a star-forming cloud. Next, it turns out that the youngest stellar objects, which are not yet fusing hydrogen to helium, radiate most of their energy at infrared and even far infrared wavelengths, unlike the sun, whose peak energy output is at visible wavelengths. Furthermore, diagnostic spectral lines radiated by hot molecular and atomic gas have their transitions in the near and mid-infrared, and warm dust in the innermost region of planet-forming accretion disks also radiates most brightly in the near-infrared. Interstellar dust particles contain carbonaceous compounds, silicates, and may be coated with various ices, depending on their location in a protostellar infall envelope or accretion disk. Their characteristic oscillations occur at near and mid-infrared wavelengths. A plethora of molecular species diagnostic spectral lines radiated by cold gas in protostellar envelopes and from the outer regions and atmospheres of accretion disks are in the submillimeter and millimeter wavelength ranges, and the cold dust present in both protostellar infall envelopes and throughout accretion disks radiate in the submillimeter and millimeter region. This slide shows why we need infrared observatories in space and why we need submillimeter observatories at high altitudes in order to get above the Earth's absorbing atmosphere. Just like interstellar dust blocks our view into the sites of star formation at optical wavelengths, the absorption by the molecules in Earth's atmosphere blocks our view of the mid-infrared, far-infrared, and sub-millimeter sky, as you can see from this diagram. The shaded gray areas show wavelengths of the electromagnetic spectrum where Earth's atmosphere is totally or partially transparent to incoming radiation from space. Black regions indicate wavelengths which are totally blocked by Earth's atmosphere. There are only two regions which can be completely transparent to incoming radiation from celestial objects, both indicated by the white lines, at visible optical wavelengths and at the longest radio wavelengths. It turns out that the interstellar medium is also the most transparent at radio wavelengths. Chemical notation, such as CO2 for carbon dioxide, H2O for water, O2 for oxygen, and O3 for ozone, indicates the atmospheric molecules responsible for blocking light at the indicated range of wavelengths. So in this optical image of our galaxy, the sites of star formation appear as black patches obscuring the light of background stars. The dark patches are composed of minuscule interstellar dust particles, which are commingled with extremely low temperature molecular hydrogen gas, 10 to 20 kelvins above absolute zero, or about minus 440 to minus 420 Fahrenheit. This material makes up giant molecular clouds, which encompass hundreds of thousands to a million solar masses and are distributed along the spiral arms of the Milky Way. It is within such structures that young stars are born. The locations of a few well-studied star-forming regions are indicated on this image. The high-mass star-forming regions, Orion A and B, W1 and W44 are high-mass star-forming regions. When we say high-mass stars, we mean those exceeding about 8 solar masses, corresponding to spectral types B1 and earlier for main sequence stars. High-mass stars are much more rare than sun-like stars. Red dwarf stars generally weigh just a few tenths of a solar mass and are the most common stars in the galaxy. High-mass stars form in large groupings in giant molecular clouds, along with many low-mass stars. Low-mass stars can also form in smaller molecular clouds consisting of just a few thousand solar masses of gas. Examples of low-mass star-forming regions are the nearby Taurus and Perseus molecular clouds, way over on the other side there, and the Lupus and Ophiuchus clouds. We'll next explore star formation in the Ophiuchus molecular clouds, which are outlined by the little cyan rectangle. Even as recently as the 1940s, the idea that stars may currently be forming was not yet generally accepted. This all changed with the discovery of deeply embedded infrared bright sources in dark molecular cloud cores. At left, you see a visible light color image of the Ophiuchus dark clouds. Due to their proximity, at a distance of just 410 to 450 light years, they've been extensively studied. Equivalent objects located at greater distances would be much fainter and viewed in much less detail. The white rectangle overlaid on the optical image is centered on what is known as the Rho cloud core. This area is expanded at right. The background grayscale image is a negative from a red filter image taken from the Palomar Observatory's second sky survey. The black contours represent the 2.7 millimeter emission of the carbon monoxide molecule, which is a proxy tracer of the molecular hydrogen making up the mass of the cloud. The visual extinction in this region is extreme, 40 to 100 magnitudes. The black square demarcates the area covered by the first systematic near-infrared survey of the row of cloud core. The 20 infrared bright objects discovered in this survey are young stars, whose locations are indicated by the black crosses. These objects are named WL1 through WL20 in recognition of Wilking and Lotta, who carried out this survey. In this slide, we outline our current picture of star and planetary system formation and how it was arrived at. Since young stellar objects radiate most brightly at infrared submillimeter and millimeter wavelengths, the crucial observations necessary to arrive at this picture were made by the launch of the first infrared astronomical satellite, IRAS, and the deployment of dedicated sub-millimeter telescopes, such as the James Clerk Maxwell sub-millimeter telescope atop Mauna Kea in Hawaii. Both of these facilities are pictured in the left panel. IRAS was launched in 1983 and mapped the entire sky at 4 mid and far infrared wavelengths at 12, 25, 60, and 100 microns. The JCMT came online in 1987. Combining IRAS observations of embedded sources in the row of cloud core. Oh boy.
I don't know what it is.
What happened?
It's coming back. Here it is. Oh, here.
Okay. Sorry about that.
You know, it's this theater.
Okay.
I thought it was me.
All right.
What did I do?
So we're getting back
Randall.
to combining the IRAS observations of the embedded sources in the row of cloud core with the ground-based near-infrared data I just showed. Those combined provided complete measurements of the total energy emitted by each young stellar object and its environment across many wavelengths, this so-called spectral energy distribution. The result samples emission from different physical structures. Near-infrared radiation is sensitive to the hot dust in disks as well as to their scattered light. Mid-infrared samples warm dust in disks, and submillimeter detects cold dust structures, including protostellar infall envelopes. Assuming different input physical configurations, such as a central star and disk and infall envelope, or just a central star and disk, and varying the inclination angles of the system, computer models of the expected spectral energy distributions were calculated. Comparison of the computed results with the observations led to the classification for classification scheme for young stellar objects still used today and shown in the cartoon schematics in the slide. Pictured here is an artist's conception of the currently understood phases of the formation of a low-mass stellar system and its attendant planetary system. Starting from a dense molecular cloud core containing a few solar masses of gas, which itself is embedded in a much larger interstellar molecular cloud, if the conditions are just right, say if a shock wave passes through and compresses the gas, the core becomes unstable against gravitational collapse and forms an actively accreting protostar. A protostellar system consists of an embryonic protostellar core which is growing in mass via the accretion of material from a surrounding accretion disk, which is itself created and maintained by the infall of material from the surrounding protostellar envelope. The accretion process generates powerful bipolar jets and winds, which carry away the excess angular momentum and gravitational potential energy, allowing the collapse to proceed. The discovery of the very youngest protostars, aged just 10,000 to 100,000 years, required sub-millimeter observations, in which your speaker took part, using the James Clerk Maxwell sub-millimeter telescope atop Mauna Kea, since these are so embedded that shorter wavelength light cannot get through. The bipolar jets and disk winds eventually disrupt the protostellar envelope and die down as the supply of infalling material dissipates. The accretion disk is cleared of gas and is the site of planetary system formation. Throughout this process, the central object is gravitationally contracting, being held up against gravity by thermal pressure. Eventually, the central pressure, density, and temperature of the young star reach conditions amenable to the fusion of hydrogen to helium, at which point we can say a star is born. Further progress in understanding the complex and detailed physics and chemistry involved in star and planetary system formation requires advanced instrumentation. This is where JWST and ALMA come in. Before a more detailed description of the capabilities of the JWST and ALMA, I'd like to point out what teensy patches of sky can be observed with these instruments by comparing their fields of view with that of the Orion Starblast 6. Last summer, I borrowed this Orion Starblast 6 through San Francisco Amateur Astronomers Telescope Loaner Program for our Tech Trek Star Party for 90 middle school girls held on the campus of Sonoma State University, and which I'm planning to borrow again for this year's event, scheduled for the night of Wednesday, June 25. You're all welcome to bring along your telescopes too. Come see me at the end of tonight's talk for more info on this event. Now back to fields of view. The Orion telescope's field of view approaches 2,500 arc seconds with its 25 millimeter or 30 times magnification eyepiece. The JWST's mid-infrared imager, observing in its medium resolution spectrograph mode, has a very small field of view, just 3 by 4 arc seconds at its shortest wavelengths up to 7 by 8 arc second field of view using its longest wavelength detector. The ALMA results I'll be discussing had fields of view of approximately 22 arc seconds. To drive home just how small JWST and ALMA's fields of view are, compare the sizes of the red squares. Whereas you could easily fit the entire full moon into the Orion Starblast's field, the approximately 20 arc second by 20 arc second ALMA field of view would correspond to the approximate size of the Aristarchus crater, and the JWST's MRS instrument would fit in just a small portion of the crater in its field. This means that a lot of preliminary groundwork observations must be made first at many other facilities before any follow-up JWST and ALMA observations are obtained. So now on to the JWST. It has 4 major science instruments and 4 major science themes. For the research I'll be reporting on in this talk, on the science theme of the birth of stars and protoplanetary systems, we will focus on results from 2 instruments, the near-infrared camera, or NIRCam, and the mid-infrared instrument, or MIRI. JWST is the largest diameter telescope ever launched into space, with a diameter of 21 feet 4 inches or 6.5 meters. Its primary mirror is a 6-sided or hexagonal shape made up of 18 individual hexagonal segments. To give you a sense for the size of the JWST Here is a full-scale model on the lawn at Goddard Space Flight Center with approximately 200 people. The JWST is built on behalf of 8 billion humans, more than 20,000 engineers, approximately 10,000 observers, and about 100 scientists worldwide, and 3 international space agencies. The JWST has been a long time coming. In the inset, you see yours truly presenting a poster entitled A Mid-Infrared Camera for the NGST. NGST stood for Next Generation Space Telescope. This was at the NGST Science and Technology Exposition in Hyannis, Massachusetts, held in September of 1999, more than a quarter century ago. So infrared observations mean that the telescope and its instruments operate at frigid temperatures, minus 393 Fahrenheit for the near-infrared instruments, and minus 447 Fahrenheit, or just 7 Kelvin above absolute zero, for the mid-infrared instrument. The need for such low temperatures is to avoid excess noise radiated by the telescope, its components, and the sun, the earth, and the moon. This is why JWST has its immense sun shield radiators. It always has its back pointed towards the sun, earth, and moon, the heat from which is constantly radiated back to space by the sun shield. Another crucial reason for a space-based observatory for mid-infrared observations is that the wavelength at which Earth radiates most is around 10 microns. So observing from the ground at mid-infrared wavelengths is like trying to observe dim stars during daylight. The required cold temperatures are attained by JWST's position 1,000,000 miles from Earth, far from both the Earth and the Moon. The mid-infrared instrument needs additional cooling, which is provided by its on-board closed-cycle cryocooler. The results I'll show from the JWST relating to a bona fide protostar later in this talk were acquired using the near-infrared camera, or NIRCam, in its imaging mode. NIRCam can operate from about 1 to 5 microns and provides an assortment of 29 filters from which to choose. It has a superb angular resolution in the infrared, about 1/10 of an arc second. The JWST results I'll show for a later stage young stellar system use the mid-infrared instrument, MIRI, in its medium resolution, or MRS mode, medium resolution spectrograph mode. MIRI operates from 5 to 28.5 microns and provides slightly worse angular resolution than the near-infrared instrument, but at stupendous sensitivities unattainable from ground-based observations. In its MRS mode, each image pixel contains a full spectrum from 5 to 28.5 microns. As we previously noted, a sub-millimeter telescope requires a high dry sight to be above most of Earth's absorbing atmosphere and avoiding water vapor absorption. This is why ALMA is built on the Chinantor Plateau at an elevation of 16,500 feet, or 5,000 meters, in the Atacama Desert in Chile, which has an average annual rainfall of 2.8 inches. ALMA uses 66 high-precision dish antennas of 2 sizes, 54 that are 12 meters across, or about 39 feet, and 12 that are 7 meters across, or about 23 feet. Assuming everything else being equal, the sensitivity of a telescope depends on its collecting area, a stupendous 71,000 square feet, or about 1.6 acres for ALMA. Now, a bit of how an interferometer works. Basically, an interferometer is a spatial filter. ALMA is trying to mimic a single 10-mile diameter antenna, which of course is impossible to build with the precision of the surface that's required. So instead we have the 66 smaller antennas. The rotation is used to effectively fill in some of the missing area from the hypothetical giant antenna. ALMA can actually attain the angular resolution of a single 10-mile diameter antenna, since its angular resolution is determined by the ratio of the observed wavelength to the maximum antenna separation. Since the maximum antenna separation is 16 kilometers or 10 miles, ALMA can attain resolutions more than 4 times better than the Hubble at its shortest ultraviolet wavelengths. Because ALMA is not a single giant antenna, it does have a blind spot. This is called its largest recoverable scale. This is a direct consequence of the fact that there's a minimum antenna-to-antenna separation. So angular scales corresponding to what could be sampled by closer antenna separations simply cannot be observed. This is caused by the physical fact that if you space the antennas any closer, they crash into each other. This limits the sensitivity of any ALMA observation to a maximum spatial extent. So if a source has structure on a larger angular scale, then it will not be detected by ALMA despite its presence. For the ALMA observations of the protostars and young stellar objects I'll talk about, this corresponds to about 4.5 arc seconds for the 1.3 millimeter observations. The third important angular scale for an interferometer is its primary beam, or field of view. As we previously saw, at 1.3 millimeters, this is about 22 arc seconds for ALMA. Similarly to the medium resolution spectrograph on JWST, ALMA acquires spectra at each image location. Although ALMA enables observations spanning the 0.3 millimeter to 3.6 millimeter spectral range, the observations I'll be reporting on in this talk were acquired at wavelengths of 1.3 millimeters and 1.9 millimeters, which are sensitive to emission from the cold dust and protostellar and protoplanetary disks, and from the cold molecular gas within them. So we'll now explore the powerful combination of JWST near and mid-infrared observations with ALMA's millimeter, sub-millimeter ones for 2 young systems in the Rho Ophiuchi molecular cloud core, a protostar and a later stage T-Tauri system. So this slide emphasizes the dramatic difference between optical and mid-infrared observations to drive home the point of why observing in the mid-infrared is so crucial to study star formation. The Rho star forming region, as previously stated, is among the closest to Earth at a distance of 400 or 450 light years. It's a favorite of amateur astrophotographers. At left, you see a colorful picture of the Rho cloud core at optical wavelengths in the range of 0.5 to 0.7 microns. By eye, Rho Oph is the blackest region seen against the Milky Way due to the obscuration of its interstellar dust. At right, you see the same region of sky imaged at mid-infrared wavelengths ranging from 3.6 to 8 microns by the Spitzer space satellite. The mid-infrared image reveals many fuzzy reddish and pinkish objects. These are young stars forming in the cloud core. We can see these in mid-infrared light for 2 reasons. Light at mid-infrared penetrates the intervening dust further than optical light can, and these objects radiate most of their energy at these wavelengths. We will next show combined JWST and ALMA results for the protostar known as VLA 1623, whose location is indicated by the small black circle. The expanded region surrounding the embedded protostar known as VLA 1623 at the location of the small black circle in the Spitzer mid-infrared image at left was observed with JWST's near-infrared camera NIRCam at right. The JWST NIRCam images is a composite of 5 different images acquired through 5 individual filters. These 5 filters included 3 wideband filters centered at 2, 3.35, and 4.4 microns, bracketed by 2 narrowband filters, one centered on a certain transition of hydrogen at 1.87 microns and the other on a specific molecular hydrogen line at 4.7 microns. Notice that the protostar, whose position is indicated by the white circle in the NIRCam image, is so embedded that it is invisible even at these wavelengths, despite the extraordinary sensitivity of the JWST. This is precisely why sub-millimeter observations were required to detect this protostar back in 1991 with the James Clerk Maxwell Sub-Millimeter Telescope atop Mauna Kea in Hawaii. What you do see, however, is the extraordinary detail in the shock structures of the bipolar jets driven by the protostar. Those are those red structures emanating away from the central protostar. The bright star at left, illuminating the yellowish nebula, is a young early type star giving off ultraviolet radiation, which causes the microscopic soot in the cloud to re-radiate at characteristic infrared wavelengths. Also notable are the extraordinary number of bipolar jets powered by other young embedded stars, shredding the cloud of which they're forming. All this stuff it's just everything. So all those young stars are driving bipolar clouds. Bipolar flows, excuse me. So spectroscopy is a fancy way of saying dispersing or breaking up light into its constituent wavelengths. An example is the dispersing of sunlight by water droplets to produce a rainbow. Instruments that can similarly disperse light to a greater extent use prisms or diffraction gratings. At sufficiently high dispersion, we can start to discern the fingerprints of gases produced when they either absorb or emit specific wavelengths of light. Each atomic gas has a characteristic set of discrete wavelengths at which it radiates. Similarly, each gaseous molecule emits and absorbs at wavelengths specific to it. This slide just illustrates the characteristic wavelengths at which molecular hydrogen emits at mid-infrared wavelengths at 5.5, 6.1, 6.9, 8, 9.7, and 12.3 microns in this example of molecular hydrogen emission from a bipolar outflow powered by a low-mass protostar. The various plotted spectra, plots of brightness versus wavelength, are extracted from various positions at the locations of the colored squares on the grayscale image of the integrated molecular hydrogen emission tracing the outflow in the top middle image. Spectroscopy also allows us to distinguish motion along the line of sight. A spectral line will be blue shifted relative to its rest wavelength if its emitting gas is moving towards us, as is the case for the molecular hydrogen towards the northwest of this protostar, sampled through apertures delineated by the blue squares. That same spectral line will be shifted towards longer wavelengths, or red shifted, if its emitting gas is receding from us, as is the case for the molecular hydrogen gas located to the southeast of the protostar, sampled through apertures delineated by the red squares. The point of this slide is to demonstrate how bipolar outflows from protostars are detected via emission from specific molecules or atoms in their constituent gases. So here we see the power of ALMA combined with JWST. From the NIRCam image, which is the background image at the top right, we can trace the bipolar outflows powered by the protostar and other young stellar objects in the field. We now understand after the previous slide that the outflows are observable only from the images obtained through the narrowband filters which transmit spectral line emission from specific gases. The F470 narrow filter, represented by the red color in the color composite near cam image, is centered on a specific molecular hydrogen line, and the F187 narrow filter, represented by the dark blue color, is centered on a specific atomic hydrogen line. Were we to exclude these two narrowband filter images from the combined color image, the outflows would disappear. In fact, the presence of a protostar here was first inferred from detection of its large-scale bipolar outflow discovered via its 2.6 millimeter carbon monoxide emission with no apparent source at the center. You see, the JWST cannot detect the protostar directly. It's still too dust enshrouded. However, the insets show the ALMA detections of the cold dust disks of not just one, but of several protostars, as delineated by the white contours. In fact, this protostellar system is now revealed to be comprised of 4 objects. Inset B shows 3 objects at the protostar's position. The proto-binary making up source capital A, labeled as capital A small a and capital A small b in inset B, which is separated by just 30 astronomical units, and it is surrounded by a circumbinary disk, along with a nearby protostellar companion labeled capital B. The orange cone-shaped structure detected by JWST at 4.4 microns emanating to the southeast of source AA is scattered light from the cavity created by the blue shifted outflow. A nearby protostellar companion is labeled B. A more distant young source labeled W is displayed in inset C. Referring to source W in inset C, we are seeing an edge-on disk. We know this both because of the elongated shape of its cold dust emission, as outlined by the white contours representing the 1.4 millimeter emission detected by ALMA, and from the characteristic appearance of scattered light from the flared disk's surfaces imaged at 4.4 microns by JWST, shown in orange. The images at bottom show velocity-weighted emission from cold gas imaged by ALMA of these sources in the carbon monoxide molecule, such that gas moving towards us is shaded blue and gas moving away is shaded red. By fitting the observed velocity structures of these disks, the central source masses can be derived. In this manner, the combined mass of the proto-binary is found to be about a quarter of a solar mass. The source B is the most massive at 1.9 solar masses, and source W, the edge-on disk harbors a central source with about 0.6 solar masses. As you see, real star formation is a messy process. The artist's conception of the physical structure of a protostar at left assumes a single star forming by itself. However, we know that most stars are found in binary and even higher order systems. In this prototypical protostar in the row of cloud core, we're finding that star formation proceeds from turbulent fragmentation of the cloud core's gas. Next, we'll discuss some spectacular results for the WL20 system from combining JWST mid-infrared instrument medium resolution spectrograph data with data from ALMA. Here is the expanded view of the small red source circled in white in the previous slide, also known as WL20. That object was already known to be a young triple system from previous ground-based observations shown in the top panel. Unlike the Sun, many stars are found in binary or higher order multiples. You might wonder, so what? So we have a young triple system. What's so special about it that it merits further study? The answer has to do with the peculiarity of the third southernmost component of the system. It's the faintest of the three at the shortest wavelengths, as can be seen in the 1.6 micron image at top left. However, as we proceed to longer wavelengths, this southern source gets progressively brighter relative to its northern neighbors, until at the longest mid-infrared wavelengths, it is the brightest of the three. In addition, the southern source is much more dust obscured than its northern neighbors. We estimated the age of the northern sources to be about 2 to 2.5 million years. However, the peculiar brightness behavior of the southern source at different wavelengths is consistent with the appearance of protostars that are less than 1 million years old. So how could this be? This is what caused us to take a look with the James Webb Space Telescope's mid-infrared instrument, in which we found, and that's the mid-infrared MIRI MRS view of the same field of view. We found a new companion. So the southern source is actually two. In the next slide, we'll focus on the region outlined by the white dashed lines in the new JWST image at bottom. So the next slide will just show that region. Ta-da! Here's the appearance of the outlined region from the last slide at 4 specific wavelengths at which ionized iron, nickel, argon, and neon radiate. The white circles in the neon image at lower right indicate the locations of the 4 sources. Remember, the medium resolution spectrograph provides us with the entire spectrum from 5 to 28.5 microns at each pixel. White arrows point to each of the jets to guide your eye. We were absolutely stunned when we first saw these images of the ionized twin jets in 9 different mid-infrared spectral lines emanating from each of the 2 sources, which were previously thought to be one. The jets must be extremely hot since they're composed of ions, which are individual atoms with an electron stripped away. Only the mid-infrared instrument known as MIRI in its medium resolution spectroscopy mode was capable of making these discoveries. It delivers images at hundreds of mid-infrared wavelengths of the same object, enabling the identification of gases of different compositions, since each element radiates at its own unique set of wavelengths. As mentioned previously, millimeter observations are sensitive to the presence of cold dust and protostellar disks and can penetrate intervening dust more readily than infrared light. At left, you see millimeter wave observations of WL20 acquired with the now defunct Owens Valley Radio Observatory's millimeter interferometer, which was comprised of 6 10.4 meter diameter antennas at the time. The positions of the 4 infrared sources are indicated by white crosses. Note that neither of the northern sources, whose positions are labeled E and W, were detected, and that the southern source was unresolved. At right is the ALMA image of the same target. At each of the northern sources is detected, and the southern source is well resolved. To get a sense of the power of ALMA, it took 18 hours of integration time to produce the image at left and just 30 seconds of on-source integration time to produce the image at right. Yeah. As noted in the previous slide, ALMA detected the 2 northern objects, WL20 East and WL20 West, each with disks with sizes that would extend out to just beyond Saturn's orbit, where they located in our solar system, although they could even be smaller given that they remain unresolved. Disk dust masses of just 3 1/3 Earth masses are derived for the eastern disk and 3.6 Earth masses for the western one. The lack of any detected carbon monoxide emission leads to the firm conclusion that the gas to dust ratio in these disks is at least a factor of 10 lower than the canonical interstellar medium value, meaning that in this stage of their evolution, at an age of just 2 to 3 million years, much of the disk gas has already disappeared from the protoplanetary disk. Mechanisms for the disappearance of the disk gas would be accretion to the central star, with replenishment from any circumstellar material having ceased, being shed by disk winds, or accretion into newly formed planets. The ALMA structure associated with the southern source could easily have been misinterpreted as a single large disk with a central gap in it, if we did not have the JWST discoveries of a new twin or of the twin parallel ionized jets in the system. With that knowledge, we can correctly interpret the ALMA image of the southern object as a pair of aligned disks seen edge on. Each of these disks would extend out to Pluto's orbit from the Sun, having diameters of about 100 astronomical units each. The derived disk dust masses are 24 Earth masses for the southeast component and 42 Earth masses for the southwest component. Modeling the measured ALMA gas fluxes, which aren't shown here, the combined gas mass for the twin disks is just 100 Earth masses, but the total gas mass remaining in these disks could be as little as just 2/3 of an Earth mass if we allow for selective photodissociation in the models. Basically, this means that planet formation has already taken place after just a few million years. Here we show the synergy between the ALMA and JWST observations of this young multiple system so far. At left is the ALMA image of the cold, dusty disks associated with each component of the WL20 quadruple system. At right, we have combined the jet emission detected by JWST from 3 different spectral lines, iron, nickel, and argon, superposed on the ALMA disk image. This combined image beautifully highlights how the jets discovered by JWST have their origins in the edge-on ALMA disks. But that's not the end of the story. To our amazement, JWST also revealed an hourglass-shaped biconical structure in molecular hydrogen heated to 2400 Fahrenheit, which you see in the left panel. In addition, the entire JWST field is suffused with hot ionized neon gas, which is not shown here. For reference, white circles indicate the positions of the 4 sources. The apex or narrowest part of this molecular hydrogen cone is centered on the twin sources, with the cone's symmetry axis parallel to the twin jets. Referring to the ALMA image at right, molecular hydrogen gas does not emit at the wavelengths to which ALMA is sensitive, but the next most abundant interstellar molecule, carbon monoxide, does. ALMA is sensitive to much colder gas, say at temperatures of 30 Kelvin or minus 457 Fahrenheit, which is about the ambient temperature of the cold interstellar gas out of which young stars form. Mapping the distribution of the cold cloud gas surrounding this young system, we find an almost perfect anti-correlation between the hot molecular hydrogen and the cold carbon monoxide. From these data, it is clear that not only is there no cold gas outflow associated with any of the WL20 sources, but that past outflow activity has completely obliterated the original cloud core from which the system formed, with less than just a few hundredths of a solar mass of cold gas left near the system. Here we put all of the JWST and ALMA pieces together. At left is shown the hot biconical molecular hydrogen gas in blue, with the field of view of the JWST observations outlined by the blue rectangle. In red, we see the larger scale map of the surrounding cold gas detected by ALMA. Notable is the spatial anti-correlation of the hot and cold molecular gas. The lack of any infall envelope surrounding this system means that the only source for the hot molecular hydrogen is from the disks of the system, which lie at the cone's apex. The molecular gas must originate in wide-angled disk winds. And at right is an artist's concept of the system. It shows the twin parallel ionized jets detected by JWST in iron, nickel, argon, and neon, and the twin dusty disks detected by ALMA. The hot biconical molecular hydrogen wind is depicted in magenta. The nearly complete destruction of the primordial gas clouds out of which the system originally formed, mapped from the cold gas emission by ALMA, is represented as the billowing orangish clouds to either side. In summary, we have seen the extraordinary synergy for gaining detailed new insights into the complex processes of star and planetary system formation by combining observations from the James Webb Space Telescope and the Atacama Large Millimeter Submillimeter Array, the former tracing hot and warm components of gas and dust, the latter sensitive to much colder material and penetrating deeper into star-forming cloud cores. Thank you.
We do have time for questions.
Yes.
How was the aim? I mean, these are discs.
Yeah.
How do you know that it's in the part of the sky you're looking at?
Well, they're all pointed at the same source when almost working, and it's highly, highly computerized and complex. Just put it that way. It, I mean, all the time they're doing calibrations of the pointing, and they have calibrators and stuff. So it's basically all computerized and very complex.
Yes, it's moving.
Yeah, well, yeah. Once they've acquired an object, then they track it pretty much automatically altogether. Yeah, they're alto-azimuth telescopes, so you get into trouble if something's directly overhead. It starts spinning. But yeah, no, it's very, very complex. Yes.
Those little PLA stars, 30 astronomical units apart
Yeah.
from one another, is that common?
Yes, actually it is.
Wow.
Yeah, there are quite a few binaries of that separation. Yes. Yes.
How is large mass star formation different?
I'm sorry, I couldn't hear you.
Is large mass star formation different?
Yes, it is. That's why I didn't get to it. Basically, high mass star formation is way more difficult to both observe and to model. First of all, the nearest high mass star forming region is Orion, so that's already quite a bit further. It's about 3 times further than this one. And second, well, many reasons. High mass stars seem to form together, like a lot of them form together, and there are even higher incidence of binaries in high mass stars than in lower mass stars. And they actually start fusing while they're still forming. So they're already fusing hydrogen while stuff is still falling in. And it's really I would say, a difficult problem of how it is that they can acquire their high masses, because you'd expect the radiation to just blow everything out. So people have tried to model the infall as maybe happening through disks, and the disk might somehow shield the radiation to allow the infall to proceed. But it's those are the the most obvious complications I can think of right offhand of high mass stars forming. But it's actively being researched. It's just even more complicated than the low mass stars. Yes.
Okay, so this is super interesting. I'm curious if you were like
like cases do we have so far of combining JWST and ALMA that are like this successful and like helpful? Like, is this we have like a few cases where we've had the resources to focus on it, or are there like dozens of stories that it's interesting?
Okay, well, let me just tell you a little bit about astrosociology. It's almost impossible to get time on either of these telescopes, and it's absolutely impossible to get time to observe just one source like this. I tried, I didn't get any time on ALMA, but the ALMA data I showed were subsequently observed by different groups who were doing big surveys of many objects. With the James Webb Space Telescope, the only reason we got time is because one of my collaborators was an instrument scientist on this MIRI, from 25 years ago. So all of the people who worked on the instruments got guaranteed time observing for the first year. So we snuck this source in there in his guaranteed time. But in general, what is spectacular about combining JWST and ALMA, a lot of it has to do with the chemistry, which I didn't touch upon at all. But there are all sorts of, oh, shoot. There's all sorts of chemistry going on in these disks that you can explore with ALMA and with JWST combined. And JWST can actually detect ices in the envelopes of protostars. And it's so sensitive. So different ices have different sort of wideband spectral features. And from modeling ices in the lab, um, you, they actually have just detected complex organic molecules in the ices from the JWST spectra, and then you're not sensitive to ices with ALMA, but you can see the cold gas, and so you can get a sense of where in the disk the ices are forming, where the gases relative to the ice. So there's all sorts of pretty amazing synergy between the two instruments. So there's a lot, but you have to apply for time individually to each of them. Okay. Yeah, one more.
What is the Nancy Grace Roman telescope going to do for this field? It's an infrared telescope, right? With a big field of view.
It's a big field of view. That's actually an interesting question that I confess I haven't given a lot of thought to, because it's mostly, from what I understand, designed to look at the shapes of galaxies to determine the distribution of intervening dark matter. But I think I'm sure there are projects that are thinking about how the data from that telescope could be used. One thing I can think of right away is variability studies, or maybe studies of, because these objects do vary, and you can learn a little bit about accretion, variable accretion, from maybe a longer baseline set of observations of the same objects, which we haven't really done systematically yet. So that's at least one thing I can think of off the top of my head. But people sit around and think these things through, and I'm sure there are a lot of projects. Yes.
Back in the 90s, before they discovered the twins,
Uh-huh.
were there any theories as to why it was brighter? Did they just
As to why
it appeared? They thought it was one star, right? Or it just
this one particular source?
yeah.
Yes. Basically. Yes. I mean, let's go back to maybe about the 1920s, 100 years ago. People were still arguing whether these regions of dark in the star field in the Milky Way were holes, actual holes, or dust. So we've come a long way. But yeah, as the instrumentation got better, that's how we learned that there were more components than just one. I mean, the first observations I showed you where it was just little crosses in that first near infrared survey, it was a bolometer observation. It was a 6 arc second detector, so you couldn't detect anything closer in than 6 arc seconds. So if you had many sources in just that one 6 arc second beam, you think you saw one source. So we had to wait for near infrared imagers, which appeared in the late 1980s. Yes.
Is there a way to understand the velocities of cold gases as they're like the three-dimensional velocities?
Yeah. Well, the three-dimensional is pretty hard. Well, okay. Like these outflows, you actually, there are time, how shall I say, time series, which I didn't show, but from Hubble Space Telescope, there are time series um, observations spaced by years of one of these outflows, and you can see the shocks moving out.
What of the darker gas?
The darker gas, you see, in order to get 3D, you need the tangential motion, and the only way to do that is if you look spaced by years apart, and then you can add in the radial velocity. So it's doable for the outflows. For the disks, I mean, as I showed, you can already see the rotation. It's pretty cool. I mean, those are very recent results. They're from 2024. Yes, sir.
Yeah, maybe I don't know if I understood your answer to this gentleman's question. So is this you're saying this is the first and the last time that these two telescopes were used together? Like it's only happened once?
No.
Oh, okay.
It's two for me. No. They're used, data from them are used together all the time. And the thing with ALMA is there's so much data. It's so much data that if I were research, and in fact I was researching now, I didn't even have to take data. They've already observed it. Someone's already observed it. So you just go into the archive. So if you have some JCMT data on whatever, you can a lot of the time just go into the archive and see if your object's been looked at and combine it that way. So there's a lot.
Did you say the protoplanetary formation was just a few million years
Yes.
old? So
that's really new.
Normally expected to be 10 times that.
Yeah, people in the older days thought that it took a lot longer for the planets to form. Well, I mean, it still does for the full formation of the Earth. It takes about 30 million years, but still, things like Jupiter and Saturn, they form on a time scale of just a few million years, and that's a pretty new discovery. People hadn't anticipated that yet, and in fact, I didn't show that, but there are some ALMA observations of really even younger sources that already have they can actually now detect with ALMA actual planets accreting gas from within their disks. It's pretty phenomenal. Yeah.
Well, could you share one other very surprising finding, perhaps, from this most recent research for you?
Well, let's see. The planets. Well, I was pretty surprised. There's many, but the fact that most of the gas in these disks is gone already. That there's so much. There's dust. There's a few Earth masses of dust, or tens of Earth masses of dust, but a lot of the gas is gone. So that's pretty new, and I think it's been seen in some other young disks in this particular cloud as well. But and also the fact that you really will have to take into account the influence on the chemistry and the planet formation of these outflows, because the planets are forming while the outflows are active. So there's a lot going that hadn't been considered before. Yeah. Yes.
So the reason that the gas is gone, but the dust is still there, is the gas is lighter?
Oh yeah, and it's blown away, and also yeah, it's right. Well, after a certain size, the dust decouples from the gas because it's heavier, just like, dust settles under our beds, right? It's not, yeah, but literally, the smaller dust is still up in the air, bouncing around, but the larger dust settles, and that's exactly what happens in these disks. The larger size dust settles to the midplane, and then it aggregates together and gradually grows up into larger and larger things to aggregate and bump into each other and build planetesimals, and then they crash into each other and build planets. Yeah.
Does the gas also escape because it's ionized? Does that play a role?
I have to, well, yes. Yeah, because the ionization, it's hotter, therefore it's so the mechanism by which these disk winds appear actually has to do with the interaction of the magnetic field with the ionized gas. And there's a whole field of computational magnetohydrodynamics that deals with that process. So yes, ionized gas gets blown away much easier. The neutral gas has to bump into the ionized gas in order to be blown away, but the ionized gas definitely has an easier time escaping.
Yeah.
Any other questions? Thank you.
You talked about a number of questions that we'd love to talk about. We do want to thank you very much. We appreciate you coming out and for making the drive down. You didn't tell us much about Tech Trip.
Okay, so yes, because
or did you?
No, I didn't really. So maybe we could be in touch via email.
Sure.
But I do want to tell you all that I'm very involved with this week-long summer STEM camp for middle school girls up in, well, actually, it's at Sonoma State University, but it takes place at 8 different campuses throughout California, but I'm involved with the one at Sonoma State. And I've taken over their star party that happens every Wednesday of their week of camp, which is June 25th this year. And because the gentleman who used to run it retired and moved to Illinois. So we had the first of these last year, and Jason and some people from SFA showed up with their telescopes, and some people from Robert Ferguson Observatory showed up with their telescopes, and there are 90 girls, and it was a blast. Everyone had a great time. So I'd like to invite as many of you as would be interested to come along. It's June 25th. It's a Wednesday night, and so maybe I can write you about it, and we can put it in your newsletter or something, or however.
Stay tuned, more to come.
Yeah. Thank you.
Thank you. And just a quick preview of the next 2 lectures. April, I don't have the date off the tip of my tongue, but it's around April 19th. Dr. Elizabeth Hawkins from the Exploratorium will be, she is also a Fulbright scholar who will be talking about her research in how the Pleiades, the group of stars, has been observed through Polynesian countries and has been used in their culture, their history, and also their agricultural practices. So that is in April. And then in May, if any of you have a telescope and don't know how to use it, a panel of SFAA experts will be here presenting 5 different types of telescopes, advantages of them, and also having a question and answer for anyone who wants to know if they wanted to get their own telescope, which is the best one. So I air quotes because obviously there's no such thing as one best, but we'll see if we can settle that anyway. So come on out next time.